All right, so I think we have a critical mass. We can get started here. Thanks everybody for coming. It's my great pleasure to introduce Chiara Mingarelli here. Finally made it to the CFA. She's going to be telling us about the gravitational wave universe. But so Chiara did her PhD at Birmingham with Alberto Vecchio.
Vecchio.
Not Vecchio. Sorry. The worst American. Or just a normal one. Anyway, okay. PhD with Alberto Vecchio, and then was a Marie Curie Fellow, first at Max Planck at Bonn, and then at Caltech, and is now a Flatiron Fellow at the CCA, just down the street. So hopefully she'll be by frequently since then. And she'll also be giving the talk at the ITYC luncheon. There might be one or two other spots for dinner if anybody's interested. So just let me know. Take it away.
Thanks, Luke. Thank you again for inviting me. It's great to see so many familiar faces in the crowd, and it's great to be here. So today I'm going to start off by telling you about the gravitational wave. This is not going to be good. Spectrum. I'll tell you where pulsar timing arrays fit in, and I'll tell you about a few different flavors of gravitational waves that we're interested in with pulsar timing. So the gravitational wave background and how we can try to constrain the final parsec problem and its solutions with pulsar timing observations. And then I'll tell you about how we can look for anisotropy in the gravitational wave background, and then the ultimate anisotropy, which is a continuous gravitational wave source, a single source of gravitational waves. So gravitational waves are real, which is nice to finally be able to say. They were first detected September 14th, 2015. Sorry?
We've known that for 40 years.
Well, Hulse-Taylor, absolutely. The 1993 Nobel Prize was very encouraging, but to see a waveform is also very nice as well. And so LIGO is the experiment that detected these very high-frequency gravitational waves. And LIGO is typically sensitive to gravitational waves from stellar mass black holes, neutron star mergers, black hole neutron star mergers, and also in the frequency range of tens to kilohertz, so very high frequency. In the center, we have LISA, and LISA will be able to detect supermassive black holes, but baby supermassive black holes, 10 to the 5 to 10 to the 7 solar masses. And also there will be a white dwarf foreground, potentially, in the LISA band. And so this is the millihertz to microhertz regime. What I'm going to focus on today are pulsar timing arrays, which are in the 1 to 100 nanohertz gravitational wave regime, so very low frequency, with the most massive supermassive black holes. So these are 10 to the 8, 10 to the 9 solar masses, and bigger if they're emitting gravitational waves. And also, we're sensitive to a primordial gravitational wave background, which I won't talk about right now, but I will talk about at lunchtime. So the important thing I want to stress, which I'm sure is not news to anyone in this room, but can sometimes be a point of confusion, is that LIGO cannot see pulsar timing array sources, and neither can pulsar timing arrays see LIGO sources. You can think about this in terms of the innermost stable circular orbit of the supermassive black holes. They tend to merge at 10 to the minus 5, 10 to the minus 6 hertz, well before you ever get into the LIGO band. Also, the gravitational waves from supermassive black holes are the strongest source of gravitational waves in the universe. So the typical strain is 10 to the minus 15, whereas LIGO sources are more 10 to the minus 24, 10 to the minus 25. So the strain, which is what I have here on the y-axis, for pulsar timing is a change in time over time, right? And this is contrasted to LIGO's change in distance over distance. It's still the same dimensionless quantity, but we think about it in terms of change in time over time. I also want to mention that NASA has now is now participating again in the LISA experiment, giving the third arm back. I believe that they're contributing at a 20% level. So thanks NASA. And this puts space-based gravitational wave detectors launching at 2034. So I won't really talk about that today, but I do plan on working on LISA sources at a more appropriate time. So for pulsar timing arrays, I just want to tell you a little bit about pulsars. They're rotating neutron stars. Their spin axis is misaligned with their magnetic field lines, and they act like these cosmic lighthouses. As they spin around, you see a flash of radio waves, and sometimes in different parts of the electromagnetic spectrum. And they have very high magnetic fields. So a typical pulsar has a magnetic field of about 10 to the 12 Gauss, and the remnants from supernova explosions. But most importantly, they're excellent clocks. So until 2012, they were better than the best atomic clocks on Earth. But it's also fine that, you know, other technologies can catch up to pulsars. I think that that's fair. This is also the 50th anniversary of the discovery of pulsars by Jocelyn Bell and Anthony Hewish. And as such, I thought I'd have you listen to the first few pulsars that we know of, including the first millisecond pulsar, which is what we're interested in. So if you could hear a pulsar, well, okay, that's Vela at 11 hertz. And Crab. Maybe I should unplug it again.
Yeah, you should unplug it.
Oh, that's already the millisecond pulsar. So that's what a millisecond pulsar would sound like. Sorry for the glitch. But anyhow, it's a rather unpleasant sound for the millisecond. Pulsar astronomers in the room. Okay. The important thing about pulsars is that they're excellent timers. And the noise between the pulsars in your array should not be correlated. The gravitational waves do correlate the pulsar residuals. And so you have the gravitational wave traversing through. You can think of water waves or ocean waves passing through, and they correlate all of the timing residuals. Now, the pulsars are all in our galaxy, which makes a pulsar timing array a galactic-scale gravitational wave detector. So in order to get a better handle on this, this is a nice animation. So you have two galaxies that are merging. Each galaxy has a central supermassive black hole. And as the galaxies merge, the central supermassive black holes fall to the center of the newly formed galaxy and start emitting gravitational waves when they're separated by a few milliparsecs. These are, again, 10 to the 8, 10 to the 9 solar mass black holes. Now, the gravitational waves propagate out in all directions. You can see here the gravitational waves are modeled by this green space-time fabric. And some of them make their way towards the Milky Way galaxy, where, of course, timing millisecond pulsars. Now, the gravitational waves change the proper distance between the Earth and the pulsar, and this induces a redshift in the signal. So the signal arrives early or late, depending on the angle that it makes with the incoming gravitational wave source. Now, if you were to see this in just one pulsar, it could be anything, right? Pulsars, even millisecond pulsars, are not perfect. However, if you see this in multiple pulsars, and again you do this cross-correlation method, you can dig out the gravitational wave signal.
So the correlation comes from the fact that the Earth is common footprint to all of these
The Earth, yeah.
legs.
So
right?
the Earth,
the motion of the Earth rather than the motion of the pulsars, is it?
well, so yes, this is called the Earth term is correlated, and the pulsar terms are not correlated because the pulsars are all at different distances.
Exactly.
Right, so they don't add coherently. But you can still use that information in different ways that I can't talk about today, but I'd be very happy to talk to you about later. So.
Okay, but right now it's the Earth motion.
Right now it's the Earth's motion, it's the Earth term that's correlated between everything. However, if you can model the pulsar term, you can do a little bit better. Yeah?
Yeah, I'm still hung up on this point, but it still looks, if you look at pulsars in different dimensions,
Yeah.
you would get different Earth terms, if that makes sense. Because
No, it doesn't.
Okay.
But when
Misunderstanding that.
so the Earth term is the only thing that's correlated between all of the pulsars. If you were to look for a single gravitational wave source, so maybe I will tell you a little bit about this. If you were looking for just one continuous wave source, then the signal at this pulsar would be slightly different than the signal at this pulsar, and this pulsar, and so on and so forth. And maybe this is where you were headed with that line of thought. And that's absolutely true. And if we knew the distances to all of these pulsars, then you might be able to do a kind of phase matching algorithm to try to map out the gravitational waveform. So I wrote a paper on this in 2012, and you can really observe the dynamics of the supermassive black holes as they're evolving. And because you do this phase addition, you can even constrain up to 1.5 PN terms. But that's for a single source. For the gravitational wave background, the only thing that we're really interested in is the Earth term, because that's the only thing that adds coherently, and the pulsar terms are typically treated as noise, but again, if you can find them, you can do a little bit better. So millisecond pulsars are important because, again, they're excellent clocks. So here we have a typical nanograv pulsar J1713 plus 0747, and by typical I mean it's one of the best ones. I just want to acknowledge Megan DeCesar, who's in the room, who does a lot of timing for Nanograv. Thank you very much for timing all of these pulsars. You see here, this is the average residual, which is the expected minus the actual arrival time. And we want this to be as close to 0 as possible for the pulsar in order to try to dig out the gravitational wave signal. Here you have a back-end upgrade that happened, and you can see the residuals are all much closer to 0, which is really what we need for gravitational wave detection. There's currently 2,300 known pulsars and about 230 millisecond pulsars, but there could be 30,000 more which are detectable. So we're not going to run out of pulsars, which is another important point. There's also been another interesting way of searching for millisecond pulsars, and that's by following up Fermi-Lat sources. And so these are some of the 43 pulsars that were discovered, millisecond pulsars that were discovered by following up Fermi observations, and they're color-coded here with the radio telescopes that follow them up. Now, while there's only 43 shown here, there's currently 86 millisecond pulsars that have been found this way so far. And actually, Megan and I are working on a project where we're trying to optimize the pulsar timing array sensitivity by looking at cold spots in the sky in terms of our response to gravitational waves and finding Fermi sources there and following them up.
Excuse me, Chiara, when
Yes.
you say 30,000 detectable, is that with current technology or is that with expected upgrades?
It's the expected population, and so they're out there, and then if we can detect them or not will really depend on our technology. And so this would be, for example, SKA Phase 1, large other survey instruments that could possibly do this.
So we're talking about something in the next decade or
And,
so, we
yeah.
could have 30,000. Wow.
That's right, that's right. So those would be pulsars, so I would say maybe 10% would be millisecond pulsars, and so that brings us down to 3,000, and then let's be conservative and say a third of those would be good enough for our experiments. That's typically the case now, but that would still put us 1,000 millisecond pulsars that are really good timers for gravitational wave experiments. Yeah. So the radio telescopes that we currently use to time these pulsars are distributed all over the world. So in North America, we have Arecibo and we have Green Bank. And Arecibo survived Hurricane Maria, and everyone is okay, which is great.
Even survived the NSF so far.
And it even, which may be more of a feat. I have a lot to say about that, but maybe some other time. There's 5 radio telescopes in Europe that we use, and in Australia, there's the Parkes Pulsar Timing Array, which uses the Parkes telescope. And possibly the Deep Space Network, which is where JPL is really helping out. They've built a pulsar backend to put onto the Deep Space Network telescope so that when it's not communicating with satellites, you can time millisecond pulsars. Because even if you only have 5 minutes, that's a lot of cycles for a millisecond pulsar. And so this will be really, really interesting to see how this...
Is there any approach to the Chinese?
Yes, so FAST. Is already collaborating with the Europeans. So there's strong links between the Max Planck Institute and the people who are coordinating FAST. There's even a lot of Chinese postdocs that went back to China to take leadership roles in FAST, so there's very strong links, which is especially helpful in navigating the politics in China. And then there's also going to be NEARCAT, which should start taking data in April 2018, according to the current predictions. So,
Where is that?
in South Africa.
That's a precursor for the SKA.
That's right, it's a Pathfinder telescope. So, in terms of detecting the gravitational wave background, we're probably used to, by now, looking at these chirping waveforms, right, and hearing everyone go, whoop, right? But for pulsar timing and for gravitational wave backgrounds, the equivalent waveform is called the Hellings and Downs curve. And what this is the expected correlation between all the pulsars when you do cross-correlate them, if you assume the background is isotropic and that it's the one predicted by GR with plus and cross polarizations. However, these are all very iffy, right? So what if the background is not isotropic? I also want to highlight that each one of these points on the curves is a pulsar pair. So if you have pulsars that are separated by about 30 degrees, then you get a correlation of about 0.3, and so on and so forth. And in the future, when we have thousands of millisecond pulsars, this curve will be perfectly sampled, and this should pop out from the data when we cross-correlate all of the data points. So this is our smoking gun signal for the gravitational wave background.
What is the overlap reduction function?
It's the word that physicists use to describe this correlation function. So we call it the Hellings and Downs curve. However, if you're talking to a room full of people who don't know who Hellings and Downs are, and you want to tell them what they did, they computed the overlap reduction function for these pulsars. It's just the correlation function. It's just another word to try to reach as many people in the audience as possible. So if, oh, this didn't come out very well. However, if the background is not isotropic, if you have any kind of departure from isotropy, 30 years after Hellings and Downs proposed this isotropic overlap reduction function or correlation function, I wrote down the first analytical terms for the dipoles that you might see in the background here in 2013, also quadrupoles, octopoles, and so on and so forth. You have to stop somewhere, so I stopped at L equals 3. And you can now use these to search for anisotropy in the background, and I'll show you the first upper limits from nanograv on anisotropy in the
So
background.
anisotropy would be a result of a nearby source, or what would be?
It could be a nearby source. It could also be due to clustering of a bunch of sources. It could also be due to Poisson noise. It could be due to faint sources that are nearby, not quite individually resolvable, but that would add a kind of popcorn noise on top of the background. There's a few different ways that you can get anisotropy in the background. So to tell you a little bit more about what we're looking for with the gravitational wave background, we compute something called the characteristic strain. Now, the characteristic strain is the energy that's summed up over all masses and over all redshifts. And the reason that this is interesting for a broader community is because it really depends on the number of merger remnants per co-moving volume, or the galaxy-galaxy merger rate, right, which relates to the black hole merger rate. So if you can constrain what this is through your observations, then you can say something really interesting about the universe. So again, Z is redshift and M is the chirp mass. And because we only know analytically that this scales like f to the -4/3, we can say that the characteristic strain itself scales like f to the -2/3. We reported at a reference frequency of 1 over a year. And all of this unknown stuff is in the amplitude of the background, right? So all of this is A. And so if we can measure A, then we can measure potentially what the merger rate is. And for any cosmologists in the room, you can also relate the characteristic strain to the gravitational wave energy density, omega GW. So we know a lot about the amplitude of the background due to a surge in the field in the last 10 years, but we still haven't detected it, and we can learn a lot more. So the latest upper limits on this A, this amplitude of the background, come from the 3 major pulsar timing array collaborations. The EPTA, whose latest result was that the amplitude is less than 3 times 10 to the -15. Also, nanograv, our previous limit was 1.5 times 10 to the -15, although we have a paper which would be on the archive in about 2 weeks with our new upper limit on the gravitational wave background. The IPTA, which is the collaboration of all of the pulsar timing arrays, has an upper limit of 1.7 times 10 to the -15, and this is worse than the other ones because it only contains the nanograv 5-year data instead of the 9-year data. So there's a bit of a lag right now between getting your best data to the collaboration, to the international collaboration, and the kind of local tribes. So that's an issue which is currently being ironed out. And the PARCS pulsar timing array limit is 1 times 10 to the -15. And I'm going to tell you a little bit about why this is maybe a bit optimistic in a few slides. So the latest results really have a lot to do with the underlying astrophysics of the gravitational wave background. And one thing that we're really trying to focus on right now is the final or the last parsec problem. And so when the supermassive black holes sink to the center of this newly formed galaxy via a process of dynamical friction or gravitational braking, they can get to within about 1 parsec of each other, but if they are not acted upon externally by anything else, they will just stay there forever because it takes longer than a Hubble time for them to merge through gravitational wave emission only. So what gives? Are there stalled binaries at the centers of each one of these galaxies, or is there a way of overcoming this problem? One of the proposed solutions is stars. So there's a lot of stars in these galactic centers, and as the stars cross the orbit of the binary, they're slingshot out and they carry away energy and angular momentum. And if these stars are slingshot out enough, then the supermassive black holes eventually shrink to a radius where they can merge through gravitational wave emission. You can also have gas, which torques the binary, and again, similarly, the binary loses energy and angular momentum, and it can shrink to the point where gravitational wave emission is very effective at causing the binary to merge. Each one of these potential solutions leaves an imprint on the shape of the strain spectrum of the gravitational wave background. So environmental coupling, which is this blue line here, is what I'm talking about in terms of solutions to the final parsec problem. You can actually oversolve the problem. If you have so many stars that they're all crossing the binary's orbit and interacting, that pushes the binary to merge at a rate that's much faster than what you would ordinarily expect, and it doesn't spend as much time emitting gravitational waves as it should, right, per residence time, and therefore your black holes are zooming through the band, they're not emitting gravitational waves, and your signal is depleted at very low frequencies or very wide binary separations. Now, galaxy population uncertainties also play a role in the amplitude of the gravitational wave background, and by this I mean things like the M sigma or MM bulge relationship, because if the black holes are more massive, then they create a background that has a higher amplitude. And so that creates this green area of uncertainty around this f to the minus 2/3 characteristic string power law. And of course, there's, the worst case scenario for the haters. There's the supermassive black hole binary stalling, and that really just shifts everything down. So if a fraction of the supermassive black hole population stalls, then the amplitude is just completely shifted down, and then again you suffer from the same effects again. So it's represented here in pink, again just shifted completely down. So I wanted to especially highlight Luke Kelly's work where he computed gravitational wave backgrounds based on the illustrious simulation and looked at a lot of these effects, and is a member of the Nanograv collaboration. We're very lucky to have him. So there's also the shape now that we're constraining with data. So these were theoretical predictions in my previous cartoon, but we're now actually constraining the shape of the gravitational wave background with nanograv data. Now I want to highlight here that this is the measured gravitational wave spectrum in terms of putting a per frequency upper limit on each one of the frequency bins. And this curve is from a 9-year data set, which means it took 9 years to produce this one curve, and that's 9 years of data taking, that's 9 years of timing millisecond pulsars. It's a huge undertaking, and I really just want to underscore that. Now this big peak here, well, it's hard to miss, is 1 over the total observation time, is 1 over a year, and that's because we have to barycenter all of the pulsar time of arrivals, and you can't trust anything that has a period of exactly 1 year. So that's where that big spike comes from. The bucket, in turn, is at 1 over the total observation time. Now, this is the f to the minus 2/3 power law for a typical background that we would expect, and you can see that we're getting very close. And this here is when we allow an underlying model. Here we chose, this is on a 2013 model. When you look for that kind of signature in the data, and you say, okay, I'm going to ask a Bayesian question. I'm going to say, what do the data prefer? Do the data prefer having a strict power law, or do the data prefer having a model that allows a turnover at very low frequency? And while a base factor of 2 is not entirely convincing to the broader community, what it means is that the chances are 2 to 1 that there's a turnover in the gravitational wave background, which means that there's something happening, there's some sort of environmental coupling that's happening with the supermassive black holes. Now, I also wanted to mention that there's been some recent work in looking at 3-body interactions, right? So if you do have a supermassive black hole pair that stalls, and then you eventually get a 3rd supermassive black hole coming in from another galaxy merger, that interaction itself, that 3-body interaction, generates a gravitational wave background that has an amplitude of 10 to the minus 16. And so for the first time, this is a kind of guaranteed floor as to what the amplitude of the background would be, even if the most massive black holes stall. Okay. So the next result that I want to show you is still in preparation. So this is some work I'm doing for nanograv, and this is a map of the anisotropy in the gravitational wave background. So I showed you earlier how anisotropy induces different correlations in the pulsars than an isotropic background otherwise would. And so by decomposing the background on a basis of spherical harmonics, and then taking the CLM coefficients and putting upper limits on them, you can get this kind of anisotropy map for the background. Now, I want to point out, very transparently, that 1.5 times 10 to the minus 15 is the isotropic solution, which is blue, and this is very blue. So we haven't seen any screaming loud sources yet that are showing up in terms of anisotropy. But the fact that we can look for it is very encouraging. So the angular resolution right now for our pulsar timing array is about L equals 5, which is a few hundred square degrees, which is quite poor. But with SKA phase 1, we should be able to get to L equals 60, or more like tens of square degrees, which is also very encouraging. The white stars are the pulsars that we currently use in nanograv, and these are the 18 best pulsars that we use to derive the upper limits on the gravitational wave background.
What's the time scale for SKA?
For SKA, well, I mean, these are now political questions. So 2028-ish, I would say is safe-ish bet. But I mean, you can't hold my hand to the fire. If you, yeah, I mean.
I won't be around to hold the feet.
It looks like you have more classes in one hemisphere.
Yeah, this is the, yeah,
Right.
so this is
So
where the
why-
galactic center is.
So why can't you get better limits in some particular directions?
We do, and actually for continuous wave sources, this becomes very important, this anisotropic distribution of pulsars. And again, for the work that I'm doing with Megan DeCesar, we look really at this part of the sky here where we have almost nothing, and find that if we add pulsars there, we can increase our sensitivity by a factor of 2. So then the natural question is, in terms of the L's, how much anisotropy is there, or how much power can we hide in these higher order multiple moments? And for the European pulsar timing array, we could hide about 40% of the power there, and with nanograv, it's 32%. And I just want you to keep in mind the fact that our current upper limits are at 32%, because I'm about to motivate an astrophysical supermassive black hole background that's at a level that's not much less than that. Okay, so how long is it going to take to detect the gravitational wave background? And Ivy, you and I were talking a little bit about this earlier. So given the amplitude of the background, that's 1 times 10 to the minus 15, how long will it take to make a detection? So if we have large and expanding pulsar timing arrays like nanograv, we'll make a detection in less than 6 years from now. So these data were from 2016, but 2016 was using the 9-year data, and they currently have 3 more years of data, so it's kind of this nonlinear underlying process. What I really want to point out is with the Parkes pulsar timing array limit, with the 4 pulsars that they use to get their 1 times 10 to the minus 15 limit, they're never going to detect anything, right? There's a less than 10% chance of detecting something in the next 20 years if they only use their 4 pulsars. So while these 4 pulsars give really good upper limits, you're never going to make a detection with it, and this is largely due to the fact that you need to do the cross-correlation to dig out the signature, and you don't do cross-correlations when you put upper limits on the background. And so and this is completely the wrong approach for looking for making a detection, although you can do it if you're looking for upper limits. So with nanograv, the EPTA and then the IPTA, I'll really focus here on the IPTA. If you have 49 pulsars and add 6 pulsars per year at 250 nanosecond residuals, then with starting from the 9-year data, we were expecting to make a detection in about 7 years, which is the blue line, so no stalling. And then the red line assumes 90% of the binary stall. Now there's no physical reason for choosing 90% other than that's a large fraction of the population and should address issues that people have with the final parsec problem. And we found that even if 90% of the binary stall, that only delays detection by 3 years. So really, in terms of our data set as of today, which is 12.5 years long, we should really make a detection soon. I also want to point out the fact that a detection here is a 3 sigma event, and we'll see a 2 sigma feature evolving over time very soon, right? And so because these are very long time scale events, you'll see a first kind of bump, right, in the data, and then that'll get better and better and better with time. So this will not be a surprise. It won't just be a mystery, loud signal that comes out of nowhere. It expands as the square root of the time and as the number of pulsars. And so while we expect in having that kind of detection, the 3 sigma event, in say 5 or 6 years, we'll definitely see a precursor to it much longer before that. Now for the SKA lovers, this is the theorist's pulsar timing array. And that's saying that if I just turn on SKA phase 1 and I have 50 pulsars that have 100 nanosecond residuals, I can detect the background in 5 years starting from nothing, right? So if you throw away all of the other data and all of the other timing experiments, the SKA can do this completely on its own. So before moving to single sources, I just want to make sure that we're all on the same page. So I just thought I'd summarize really quickly before switching gears and remind you that pulsars are excellent clocks, and that's why we use them to look for gravitational waves. We use pulsars to look for low frequency gravitational waves from supermassive black hole binaries, and the gravitational wave background really has information in it that can tell us about the final parsec problem and its solution. And the detection of the gravitational wave background really depends on this underlying astrophysics. And that there's this regime between an isotropic background and single sources that you move through. And this is the anisotropic regime. And we're now searching for this kind of signature in the data. So the last thing I want to tell you about are individual supermassive black hole binaries. And I'll tell you how many binaries we expect to detect in the local universe, so within the 2 mass volume of 225 megaparsecs, how many of those should be detectable, and when we should expect to detect them. And so this is a really radically different approach than the approach that has been taken before. So previously, you start with a simulated galaxy population, and then you make inferences using some random distribution of pulsars that have random, or idealized timing residuals, and you make predictions about the future. My approach is the opposite way. So this is a kind of top-down approach. And my approach is to go the other way, is bottom-up, to say supermassive black holes are in massive galaxies. We know where galaxies are on the sky. I can point to them, right? This is not a surprise as to where supermassive black hole binary should be. So why don't we use this information to make predictions about the universe and about the time to detection? Moreover, I know where my telescopes can point on the sky, so let's pick pulsars from parts of the sky which are accessible with our current radio telescopes and go from there to make predictions about the background. So these results were just published in Nature Astronomy. The article appeared last week. So I'm really pleased to tell you about these results today. So I start with choosing a galaxy survey. And I chose 2 mass because it's an all-sky survey. And I didn't cut on morphological features because the time scales for the mergers are so uncertain. All I did was to make a mass cut. I said, okay, given what we know about the current black hole host relationships, how much stellar mass do I need, or what's the K-band magnitude corresponding to that, to have the massive black holes that we need for pulsar timing array detections. So I converted from a K-band luminosity, which was minus 25, and then for other more massive sources, to convert this to a stellar mass, And then from the stellar mass, I converted these to black hole masses, except if the black hole mass had an independent measurement, and then I used that. Right? So some supermassive black holes are very well measured, have very well-known masses, and when that's possible, I use that mass, and if I can't, then I use bulge. So I consider major mergers, so I limited the mass ratio of the binaries that I considered to be between 0.25 and 1. So when I was simulating a gravitational wave sky, we had to identify what the probability was of each galaxy hosting a supermassive black hole binary in the pulsar timing array band. So there are these two key ingredients. Now the first one is the probability that your binary is in the pulsar timing array band over the entire lifetime of the binary. And so essentially what that fraction is the amount of time it spends emitting gravitational waves over the entire lifetime of the binary. Right? So that's this first fraction here, that we catch it in this window when it's emitting gravitational waves. This is typically 25 million years, right? So this is not, again, like a LIGO source where it's in band for a fraction of a second and then disappears. This is, you know, some of the first kind of, you know, life appearing on Earth, you know, 25 million years ago. This is really a long time to spend in the PTA band. The second thing is the galaxy merger rate. What's the probability here, this dn by dt times tz, what is the probability that there's a binary in the first place, right? And this is where I use the illustrious simulation to say, you know, given my galaxy with current stellar mass and redshift, what is the probability of there being a binary in there? And so I got this merger rate from Rodriguez-Gomez et al. 2015, again based on the illustrious simulation. And for my sample of 5,000 galaxies, each one of them, I then computed a probability for, and the total number of galaxies that hosted binaries is the sum of all of these probabilities. Now, if this timescale was larger than 12.5 gigayears, I claim that the binary has stalled because this is redshift 4, and if it's not there by then it's probably not going to be there. So the first result is the number of gravitational wave sources per realization. There are about 91 local galaxies that should be hosting supermassive black hole binaries in the pulsar timing array band. That's 91 out of 5,000 of the most massive galaxies in 2 mass. Now, this means that they have frequencies of greater than 1 nanohertz, but it doesn't mean that they're detectable. It just means that they're in the right frequency band. The detectability issue depends on the instrument and, of course, on the strain of the binary, not only its frequency. The second result is the number of stalled binaries per realization, which is about 7. And 7 out of 5,000 is a very small stall fraction. So if we look at the final parsec problem in terms of these timescales, it's really not a very big problem at all. Now, in terms of the detectability issue, you have here the 5,000 galaxies from 2 mass, and you have on this side the EPTA's response to gravitational waves. Now this is where the distribution of pulsars becomes really important, because for single sources, your strongest response is behind your best pulsars. And so here you see this dipolar-like map, and that's because these are the best pulsars in the EPTA, these orange stars which are listed here. And you can see a factor of 4 more in terms of strain behind those pulsars than you can across the entire sky. And this is really important for making predictions about the time to detection of the background. So if you mentally convolve these 2 images, then it's no surprise that when you do multiple realizations of the universe, that most of your detected sources are over here, where you have the most sensitivity on the sky. Now, should we have detected something already? This is the kind of hair-pulling out question that one asks oneself when doing this work. And it turns out that given the current data, only 130 skies out of 75,000 contained screaming loud detectable sources. So this is much, much less than 1%. And so the fact that we haven't detected anything now is completely consistent with our data. So everything so far is fine. Now, here, this is a whole gravitational wave sensitivity map of the sky. But what we're used to looking at are these sky average strain maps. And this here is at 4 times 10 to the minus 9 hertz. And that means that one of these points, well, each one of these points, is a sky average map. So you lose all of the pulsar information when you create one of these maps in order to see what your sensitivity is across all frequencies. Now I took these points here, which were all detected using these sky maps, and overplotted them on this upper limit curve to show you just how important it is to have these sky maps instead of the sky average strain. Because you see a lot of these dots fall below the sensitivity map, so you'd think naively that you wouldn't be able to detect them. But you have this extra factor of 4, which comes from your pulsar sky location. And therefore, you can really do a factor of 4 better, especially at low frequencies in some parts of the sky. So this is really important to keep in mind. That this is the idea that we should have in our heads for our sensitivity maps, and not necessarily the sky average strain, because the positions of the pulsars matter so much when you're looking for single sources. So then what's the time to detection of these single sources? So again, I start with the 49 IPTA pulsars and expand the IPTA using their real noise properties, and I make an optimistic and a pessimistic prediction. So pessimistically, if you have strong red noise in your pulsars, which is equivalent to an unresolved gravitational wave background, then your chance of detecting something with a 25-year data set is pretty grim, right? So a 25-year data set is about 10 years from now. We're currently at about 15 years in terms of our data set. However, if you can subtract the gravitational wave background and your pulsars are white noise dominated, then with a 25-year data set, you can even detect up to 4 sources. And so what is then the average? This is just one realization of the sky. And so over multiple realizations, I summarized my results here, that for different false alarm probabilities and different lengths of data set, for white noise and for red noise, you have these predictions. So let's look at the 25-year data set, which is again 10 years from now. You have a 100% chance of detecting something at a 2 sigma level. You have about a 50% chance to detect something at a 3 sigma level, and about 25% chance with a 4 sigma detection. This is really 3.9 sigma, but you'll forgive me. And so this is white noise dominated pulsars, and this is red noise dominated pulsars. But we have to remember this factor of 4 that comes from the sky location. And that means that we essentially have a 100% chance of detecting something at a 4 sigma level in 10 years from now in the 2 mass volume. Now that's exciting because these all have NGC names, right? These are the Hubble calendar images, and some of them could have supermassive black hole binaries. And because I used real sources, I could also tell you what the likeliest K-band luminosity for the host galaxies is for the pulsars, and then also what the average distance to the sources are. But interestingly, what the average detected chirp mass was. Now, initially, when I set out on this project, I assumed that for gravitational wave detection for supermassive black holes, the bigger the better, right? The more massive the black holes, the bigger the strain. However, it looks like we much prefer supermassive black holes with a chirp mass of about 10 to the 9. And this makes sense when you figure out what the answer is. Usually, retrospectively, things are much clearer. It's because the time to coalescence scales like chirp mass to the -5/3. And so if you have very massive binaries, they zoom through the pulsar timing array band, making it very difficult to detect them. The probability that you're catching the binary at that particular moment in its life is very small. And so there's a sweet spot between having a binary that's massive enough for it to be detectable, and then also to have it not be so massive that it zooms through the pulsar timing array band. And 10 to the 9 solar masses really is that particular sweet spot. And again, because these are real galaxies, I can show you what Chung-Pei calls the hit list, Chung-Pei Ma. And the #1 galaxy that's perfect for pulsar timing is the Sombrero galaxy, which is a kind of fun result because you wouldn't expect the Sombrero galaxy to be perfect, but it is perfect. On average, it has a supermassive black hole binary that would be about 10 to the 9 solar masses and would spend about 160 million years in the pulsar timing array band. The before final slide is perhaps the next logical step, and it really sets up the rest of my work for this year, well, and next year, is what's the contribution of these local sources to the gravitational wave background. So if I have a realization here of the local universe that has a really loud source in it, and I turn all of these into a gravitational wave background, you can see that the background is dominated by this single source here in the middle. However, if I subtract it, this is the kind of gravitational wave background I get from the superposition of all of these nearby sources. Now, this again looks highly anisotropic, but how anisotropic is it? Well, if I have this all-sky map with the loud source, this is the angular power spectrum of my background, it's blue. You can see it's really dominated by this loud source, because when you subtract it, and I look at the angular power spectrum of this sky, which is orange, you can see that the average level of anisotropy is about 20 to 25%. And the current upper limits are 32% from nanograv that I just showed you. So we're in fact getting really close to being able to constrain the amount of gravitational wave anisotropy in the background from nearby local sources. So to finish, I just want to provide you with my summary notes. PTAs are an incredibly interdisciplinary experiment. I've only really talked to you about the supermassive black hole aspect of this experiment, but really, you can have radio and gamma ray astronomy. There's fundamental physics, galaxy evolution, supermassive black hole environments, propagation of these signals through the interstellar medium. There's really something for everyone in these experiments. We're already placing astrophysical constraints on binary environments, and EPTA and nanograv have limits on the anisotropy in the background. The evidence for the background should appear in terms of a detection at a 3 sigma level in about 5 years. But again, the 2 sigma detection, well, the 2 sigma feature, let's call it, would come first. And for local sources, we can have a very strong detection in about 10 years. Importantly, we can now build gravitational wave skies from galaxy surveys and create backgrounds. And that tells us a lot about the underlying astrophysics. So right now I've only included stellar hardening to solve the final parsec problem, but in my future work, of course, I'll look at gas, I'll look at accretion, binary eccentricity, and more. And in order for this experiment to keep going, all we need to do is to time more pulsars. So the orchestra is just warming up, and so far we've only heard the violin, right? Thank you very much for your attention.
Any questions?
Well, I'm intrigued by your result about the nearby galaxies, and in particular M104 is a great favorite. So, we know that M104 does have a supermassive black hole of a few billion solar masses. Are there observations right now that either have been done or could be done that would tell us more about whether or not there is a potential merger that could happen there?
So we did follow up. Where is it? We followed up, well, we did a literature survey of all of these sources to find out which one of them, if any, had signatures of a merger happening right now. And NGC 3115 was the clear winner there. Now, with Sombrero, I'm not sure that the way to interpret this is that there's a merger happening in Sombrero, but it's mostly the properties of Sombrero that are perfect. It's a perfect environment for a pulsar timing array binary. So it does motivate looking at it more closely, absolutely. And in fact, with the new nanograv continuous wave limits, it would be possible to effectively point and try to place really strict upper limits on any binary that might exist there. One other thing I should mention is that Changpei Ma and her student Caitlin Schutz published a paper on the most massive nearby binaries, and assuming that they were at a peak gravitational wave frequency, in turn putting a limit on the mass ratio of the binary given the current non-detection. And so we could also do something like that.
Very interesting.
like you said, the sensitivity will improve with the square root of the time and also the number of pulsars
Yeah.
we have. But could you say, is there some technological improvements that may be possible that could improve it, or is there currently a bottleneck?
Absolutely, and I glossed over it in the sake of time, but one of the technological improvements that I assumed here was a wideband timing backend that will be installed in 2018 at both Arecibo and the Green Bank telescope, and that reduces the white noise RMS by a factor of about 2, and that plays a strong role in improving the detector sensitivity. And so by having these kinds of receivers, we do increase the timing precision in our best pulsars, which is really important for making a detection of continuous wave sources.
So you said that soon we'll be able to see the 2 sigma candidates from the MPIRA.
Yeah.
I'm just wondering what the landscape looks like now. Do we have a bunch of 1.5 sigma things, or not really?
I'm not sure I'm allowed to say.
That is yes. She's not allowed to say.
So there was an interesting development that happened with the Nanograv 11-year data, and I can absolutely tell you about this because the paper will be on the archive soon. And that's that we found that there were solar system ephemeris errors that were masquerading as gravitational wave background signals. So there were some rumors that Nanograv had detected something, and it was all very exciting because we thought it was potentially something interesting. But it turned out that these solar system ephemeris errors only showed up in the 11-year data set because it's really about 11.7 years of data. And 11.7 years is also roughly the period of Jupiter. And Jupiter's mass is very well constrained, but the masses of Uranus and Neptune are poorly constrained, and they were perturbing Jupiter's orbit and making what we thought, so there was a dipole term that we usually allocate to a solar system ephemeris error. But that error was so big that it leaked into the quadrupole term, which is where the gravitational wave signal should be. But we discovered this by changing the underlying model and trying to figure out where this was coming from, because of course you have to be really sure if you're going to make one of these gravitational wave detection claims. And we found that by changing the solar system ephemeris model, that it changed our limit on the background, and the feature would show up and go away, most alarmingly. And so then we figured out now how to get rid of this additional term. And now we can use any kind of solar system ephemeris model. We've now had to revise our previous limits because we were using the kind of optimal solar system ephemeris model, which is also what the Australians were doing and what the Europeans were doing, but we just didn't know it, right? So we've now hit a new noise floor with the Nanograv 11-year data. And I think it's also really amazing that the data are now so sensitive that you have to know where the solar system barycenter is to within a few hundred meters. Right? And when we were telling this to the people at JPL, where should we balance the solar system on our finger to within a few hundred meters, they were floored. They were like, we don't care. If you send a probe to Mars, the wind's going to blow it around a bit, like much more than that. Like they basically called us geeks. And so, but they're working with us now to develop new models so that we can continue to do this work.
So how could those ephemeris issues affect the park's upper limit?
It would be, so the park's upper limit is, again, there's a few things that went wrong with that. They only used their best pulsars. They should have used more. So the backwards revision of that, I'm not sure that we're publishing it as Nanograv because it's not really up to us to do. But the 1.5 times 10 to the minus 15 upper limit that we published for the 9-year data should have really been something like 2 times 10 to the minus 15. So not a huge revision, but still, it's an honest correction that we're making.
One thing to keep in mind is that the barycenter may be accelerating to some external objects, but it's not at 100 meters over a 10-year period. It's more like 10 centimeters over 10. For example, the galaxy is accelerating in the solar system, right?
Mm-hmm.
So the barycenter will not always be in the same place over such a long period of time.
Yeah, that's right. That's right.
Depends on how many elongated asteroids.
Any last questions? All right, let's thank. Oh, sorry.
I've always been interested in one of your backgrounds, which is radio propagation through the interstellar medium.
Yeah.
And so you're detecting objects, filaments, I'm not sure what shape they are, floating across the lines of sight to these pulsars in the time dependence of dispersion measures.
Yeah.
Is somebody working out what population of these things there are?
So Dan Steinberg is doing a lot of work on modeling the interstellar medium and then also trying to mitigate for these effects. And in terms of how it affects the pulsar timing signal, this can be really significant because, as you said, the radio waves at different frequencies are affected in different ways by the ISM. And so one thing that will really help is the CHIME telescope that's coming online in Canada, the Canadian Hydrogen 1 Intensity Mapping Experiment. And they'll get very low frequency observations, and then with Arecibo we can get very high frequency observations, and then that'll really help us to understand exactly what's happening with the ISM to then subtract that signal properly.
All right, well, let's thank Chiara again.
Oh, thank you. One more and then I can eat, right?
Yeah.